Good afternoon, students. Is my voice audible? Students, is my voice audible?
Yes, sir.
Sir,
So in yesterday's class, we have seen potentiometers and introduction of the strain gauges. Here we have different types of strain gauges. This is a basic strain gauge construction, and here we have different types of the strain gauges: bonded, unbonded strain gauges, and rosettes. This figure is called as rosettes. If we use multiple wires in construction of the strain gauge, that is called rosettes. And here also we are using 3 wires, and here multiple wires we are using, here multiple wires we are using. So different types of strain gauges you can see here. Next one is semiconductor strain gauge. There are other kinds of electrical resistive strain gauges other than metal strain gauges. The measurement principle of semiconductor gauges is based on the semiconductor piezoresistive effect. The measuring element includes a strip few tenths of a millimeter wide and a few hundredths of a millimeter thick, which is fixed to an insulating carrier foil and is provided connecting leads. 1 minute, students. The measuring element includes a strip a few tenths of millimeter wide and a few hundredths of millimeter thick, which is fixed to an insulating carrier foil and is provided with connecting leads. Here you can see semiconductor type of strain gauges. I will show you images also. A thin gold wire suppresses diode effects as a connection between the semiconductor element and the connecting strip. Semiconductor strain gauges are used for measuring very small strains. The large signal given by this kind of strain gauge is beneficial in the presence of strong interference fields. So this is called semiconductor strain gauge. Here we have semiconducting material strips. If you apply strain on these strips, you will get resistance variation. And here we have different types of strain gauges. Now I will show you a video, students, strain gauge video. See students, here we have strain gauge. This device is called as strain gauge. And strain gauge has leads. That leads are connected to an electrical network. And these are the loads. We will put these loads on the strain gauge to create the strain.
A strain measurement using a strain gauge. Okay, so this is the instrument that we'll be using to measure strain. So first of all, we have to calibrate this instrument such that it gives the correct reading. So here we are having a strain gauge. Okay, this is the load that we'll apply. Okay, each cylinder is of 100 gram weight and the total weight is 1 kg. So we will take this thing here.
So he is applying that load on the strain gauge.
And we will apply the weight to this cantilever beam. Okay, and we are going to calculate
This beam is called as cantilever beam.
the strain of this cantilever beam using our instrument. Okay,
Because of this applied load, the strain is developed on the cantilever beam.
so this beam is actually connected
And inside we have resistors in the cantilever beam.
to our instrument here. As you can
This is an electrical network board. Here, strain gauge is connected one of the resistors of these 4 resistors. Initially, before applying the load, 4 resistors are same value, so electrical output will be 0. But we are applying load on the strain gauge, so resistance will vary. So we will get different outputs.
You can see the circuit of the instrument. The strain gauge is connected as a Wheatstone's bridge. Okay, and so that we need to measure, that is the strain. That voltage is amplified using, this is the instrument that is being used to measure our strain. Okay, so now let us see how to calibrate this instrument. Okay, so first of all, we'll remove this load. We'll keep it aside. So this is our strain gauge as it is. So we have applied 0 load. Since we have applied 0 load, the output should be actually 0, but it is displaying as -2. So what we'll do, we'll change the 0 balance here. Okay, this is the 0 balance calibration system, and this is the final value calibration system. So for 0 balance, we'll make, okay, now our display actually shows 0, that is a 1 kilogram weight to this strain gauge here.
Now he is applying.
And corresponding to 1 kilogram weight, actually the strain is calculated to be 377.
Output is 60 instead of 0.
The calculation is shown here.
If 4 resistors are same, output should be
6
0.
divided by BT squared by E. Okay, and the final value when we apply a weight of 1 kilogram is 377 micro. Okay, 377 into 10 raised to minus 6. Okay, so that much change in length is coming when we apply a 1 kilogram of weight to this strain gauge. Okay, so if 1 kilogram has been applied, our output should display 377. So using my final calibration, I will make this value as 377. Okay, 377 is the final value. Now I'll remove this complete load and see whether actually 0 is coming or not. If 0 is not coming, then I have to again calibrate this using this 0 setting. So I'll again calibrate this to become 0, and again I'm applying this complete weight here. So you have to do the calibration till you get the correct value for both sides. Okay, so here we are having 377. Okay, 376, 377. It is fluctuating. That will be not a big problem. Okay, so if we are having the final value as 377, let us see again what happens when we remove this load. Okay, now it's 0. Okay, now we can say that our strain gauge is correctly calibrated. Here 376, yes, we'll make it 377. Okay, 378, that will be enough. And if I remove the load, 0. If I put the load, it is 3.
Can I observe the output?
And if I remove, okay, 378, that will be enough. And if I remove the load,
if there is no load, output will be 0. If you apply load, output is varying.
0. If I put the load, it is
showing some output. So in this way, we can find out the strain by using strain gauge, and formula for gain factor is gauge factor is delta R by R divided by epsilon naught, epsilon gauge factor. And here we have semiconductor strain gauges. I will show you some images of the semiconductor strain gauges. So these are the semiconductor strain gauge. Here you can see gauges with backing. That is, this is naked gauge. If you place on the support, it will become gauges with the backing. This orange color support is called as backing. And different types of leads here we have. It is depending on the application, we can arrange the leads. Depending on the application also, we can choose naked gauges or gauges with the backing. So this is another type of semiconductor strain gauge. If you observe white color line, this is our semiconductor strain gauge. Two leads are connected to two electrical wires. If you apply strain on this white color line, you will get strain values. So this figure shows sketches of a semiconductor strain gauge. First figure is and the last figure are similar. The only one thing we have to remember in this semiconductor strain gauge is we have to use gold wire as leads. So this is about semiconductor strain gauge. And here we have details and uses of semiconductor strain gauges. Advantages: semiconductor strain gauges have the advantage that they have high gauge factor about less or minus 130, whereas in normal strain gauges we have only 2 as gauge factor. This allows measurement of very small strains of the order 0.01 microstrain. Hysteresis characteristics of semiconductor strain gauges are excellent. Some units maintain to less than 0.05%. Hysteresis characteristic we have studied in the previous module. If we increase input and if we decrease input, device has to show same values for the same input values. It has to produce same output for the same input value. It should not change in 2 ways. Fatigue life is excess of 10 into 10 to the power of 6 operations, and the frequency response is up to 10 to the power of 12 Hz for the semiconductor strain gauges. Semiconductor strain gauges can be very small, ranging length from 0.7 to 7 mm, very small size. And disadvantages: the major and serious disadvantage of semiconductor strain gauge is that they are very sensitive to changes in temperature. Linearity of the semiconductor strain gauge is poor. The equation for the fractional change in resistance is delta R by R. That is mathematical expression. No need of focus on the mathematical expression of the semiconductor strain gauge, because already we have seen the expression of the gauge factor in the strain gauge. Semiconductor strain gauges are more expensive and difficult to attach to the object under study. Very sensitive and very weak. So we have to handle with care semiconductor strain gauges. They are very, very tiny objects, so we have to take care of their working. Next type of resistance type of resistive type of sensor is RTD. We have completed experiment also. So here full form of RTD is resistance temperature detector. Directly we have to insert a resistive material in a pipe type of thing, and we have to place that pipe to high temperature, that pipe in high temperature areas or lower temperature areas. Depending on the operation, we have to choose RTD. Most of the RTDs use platinum pipe. When if you place that RTD at higher temperatures, RTD resistance will increase. If you place RTD at lower temperatures, its resistance will decrease. So here we have different types of materials: platinum, nickel, copper, ball point, tungsten. And at higher temperatures, if you want to calculate, we have a formula, that is RT is equal to R naught into alpha into T minus T naught, whereas RT is the resistance at a given temperature and R naught is the resistance of the RTD at 0 degrees Celsius. Alpha is the resistance temperature coefficient. Temperature coefficient of resistance or resistance temperature coefficient. And T is the room temperature or oven temperature, and T naught is the initial temperature. The criteria for selecting a material for RTD: malleability to form small wires, linear relationship of resistance and temperature, repeatability and stability. We have focused on the repeatability in the previous module. Corrosion, we have to take care of materials which we are using in RTD, and we have to focus on the cost, and we have to focus on the availability of the different metals which we are using in the RTD. So here we have platinum leads, and this is resistance material, ceramic material. We are winding the resistance wire and protecting case, and this is the image of the RTD. This is internal structure of the RTD. In this pipe, we have this type of ceramic bed and wounded wire on the ceramic bed. And this is construction of the RTD. RTD lead seal, RTD probe sheet, RTD sensing element, thermo well. So inside we have to place our resistive material. We'll see the RTD video. So here we have RTD experiment video. And these two are two RTDs.
From minus 260 degrees centigrade to 1000 degree centigrade. And the materials that are used for its construction are mostly platinum, copper, nickel, or sometimes alloys are also used for its construction. So different metals are having different melting points. So that's why.
So with this electric stove, we are making hot water. In this hot water, we are placing our RTDs.
The material which is used for its construction, depending upon that, the temperature ranges of that RTD changes. Okay, so here you can observe this is whole setup for RTD where we are going to study the temperature versus resistance characteristics of this RTD. Here we have this RTD, this is nothing but the RTD, these two leads. One wire from this one lead is connected over here at the RTD where we are going to measure at this terminal, we are going to measure resistance across this RTD through this multimeter. तो इस टर्मिनल के अक्रॉस मल्टीमीटर भी लगाया है जिससे हम रेजिस्टेंस मेजर कर सकते हैं RTD का. As well as another terminal, two wires are there from this RTD. Another wire is given here at this terminal where we are measuring the temperature of this water. Here in this pan we have a water. Now it is having a room temperature and this is nothing but a heater. With the help of heater we are going to raise the temperature of water. So as soon as we start heater, the temperature starts changing of this water and that temperature is going to be displayed over here. And as per the temperature changes, that temperature is sensed by this RTD. So here the sense temperature, as per the sense temperature, the resistance across this RTD changes and that resistance is reflected in this multimeter. So what we are going to measure is for corresponding temperature, for this change in temperature, corresponding resistance of that RTD, change in resistance we are going to measure. Okay, and we are finding corresponding resistance for the particular temperature. Okay.
See how
Then
temperature
observe
is
before starting
increasing,
heater,
31 to 32.
this display gives the 32 degrees centigrade, that is nothing but the room temperature.
So keep
It is showing
on increasing
32.
temperature
So
of the
this is nothing
water
but the room temperature of water. Okay, and corresponding resistance
by
at
using
this room
multimeter. We
temperature
can
for
estimate the
RTD.
resistance.
You can see here, this resistance is 112.5 ohm.
So
this is the
initially
first
our
reading for the
resistance is 100 ohms. Now it is 112 ohms.
room temperature. Temperature is 33 and corresponding resistance is 113.4. Okay. Now we are noting this first reading in the observation table. So here your first is 33.8. Start heater, you can increased. Okay. Initially 33 to, so in a
Now
difference
temperature is
of
34.
2,
We'll see how the
we'll take
resistance will be.
temperature reading and its corresponding resistance. Now it is changing from 33 to 34. You can see here. Now it's 35. So second reading is 35 for 35 degrees centigrade temperature. Corresponding resistance, you can
114
observe, it is
ohms.
114.6. So we'll in difference of 2, 37. We'll write 37.
For 37
For
degrees
37
Celsius.
we note down the corresponding resistance, that is 114.6 or 114. Okay, readings, similar 10 readings you can find that the temperature versus resistance characteristics of RTD is almost linear. Okay.
So there we are using RTD to estimate hot water temperature and its resistance correspondingly. There are different points about the RTD. Very high accuracy and excellent stability and reproducibility. What is meant by reproducibility? If you use the device at different time periods, it has to produce same output for the same input values. And good interchangeability. Next, susceptibility to mechanical damage. It has to bear different kinds of situations during the operation. Need for lead wire resistance compensation. Sometimes expensive, with a temperature range up to 850 degrees Celsius. RTDs can be used in all but the highest temperature industrial processes, that is 850 degrees Celsius. They are used in air conditioning and refrigeration applications. To measure surface temperature of materials, they are used in exhaust gas temperature measurement. These are the few points about the RTD. So here we have different types of RTDs. Platinum sensors for temperature probes use wound, and second one film resistive. Anything we can use depending on the application, depending on the operation. For immersion in fluids, there are models that consist of a thin wire non-inductively wound around a ceramic form to allow some relative movement in order to make room for differential expansion. For immersion in fluids, there are models that consist of a thin wire non-conductively wound around a ceramic form here to allow some relative movement in order to make room for differential expansion. Surface temperature sensing RTDs can also be mounted similarly to strain gauges, and they can also be formed by parallel wire, foil, or deposited metallic form. So these are the two types of Rtds which are useful in different applications. Another type of Rtd here we have, that is a catalytic gas sensor based on sintered bead with a embedded coil of platinum wire. Catalytic gas sensors use a fine boil of platinum wire and measure its temperature when heated about 450 degrees Celsius. Here we have platinum wire. The coil is embedded in a pellet or bead of sintered aluminum powder called a Thermistor. Here we have platinum. Impregnated by a catalyst. If a flammable gas contacts the catalytic surface, it becomes oxidized. Flameless, thus increasing the temperature of the wire by a few degrees, hence its resistance will increase. In order to compensate for ambient temperature and humidity interference, a similar Thermistor but without any catalyst is placed next to the active Thermistor and series connected to it, thus forming a half bridge. So this is one type of Rtd to estimate the quantity of the gas. If you place oxidized material, when this gas mixes up with this material, it will get heat energy, and because of that, resistance wire resistance will increase. This is about Rtd. Introduction of the Rtd, structure, construction of the Rtd, and types of Rtd. And next device is called Thermistor. A thermistor is defined as a type of resistor whose electrical resistance varies with change in temperature. As it is in the Rtd, thermistor also will get change in its resistance if you increase or decrease surrounding temperature. Although all resistors resistance will fluctuate slightly with temperature, a thermistor is particularly sensitive to temperature changes. It is very sensitive. Thermistor is very sensitive for the temperature changes. Thermistor acts as a passive component in a circuit. They are an accurate, cheap, and robust way to measure temperature. They are an accurate, cheap, and robust way to measure temperature. While thermistors do not work well in extremely hot or cold temperatures, they are the sensors of choice for many different applications. Thermistors are ideal when a precise temperature reading is required. So if you want to estimate temperature precisely, you have to prefer thermistor because they are very accurate and they are very sensitive. Since the resistance of thermistor is dependent on the temperature, they can be connected in the electrical circuit to measure the temperature of the body. The resistance of the thermistor is given by R is equal to R naught into e power k, where k is equal to beta into 1 by T minus 1 by T naught. 1 by T minus 1 by T naught. The working principle of a thermistor is that its resistance is dependent on its temperature. We can measure the resistance of a thermistor using an ohm meter. If we know the exact relationship between how changes in the temperature will affect the resistance of thermistor, then by measuring the thermistor's resistance, we can derive its temperature. How much the resistance changes depends on the type of material used in the thermistor. The relationship between a thermistor's temperature and a resistance is non-linear. A typical thermistor graph is shown below. Here you can see the graph of the variation in the temperature, variation in the resistance depending on the temperature. If we had a thermistor with above temperature graph, we could simply line up with the resistance measured by the ohm meter with the temperature indicated on the graph. By drawing a horizontal line across from the resistance on the y-axis and drawing a vertical line down from where this horizontal line intersects with the graph, we can hence derive the temperature of the thermistor. Different types of the thermistors here we have. Images shows different types of thermistors. I will show you thermistor IC also. So in our laboratory, we use thermistor ICs. The thermistors are made up of ceramic-like semiconducting materials. They are mostly composed of oxides of manganese, nickel, and cobalt, having the resistives of about 100 to 450,000 ohm centimeters. Since the resistivity of the thermistor is very high, the resistance of the circuit in which they are connected for measurement of temperature can be measured easily. This resistance is calibrated against the input quantity, which is the temperature, and its value can be obtained easily. So here we have different thermistors. I will show you IC of the thermistor now. These students here we have different types of metals and different oxides are bonded in a ceramic coating. All these are thermistors. All these are thermistors. And here you can see NTC. Full form of NTC is negative temperature coefficient. Negative temperature coefficient. In coming slides we will see Ntc and Ptc thermistors. So these are the ceramic type of thermistors, and ICs I will show you now. And these are the ICs. Thermistor ICs. And this IC has only 3 pins. Here you can see 3 pins IC. With these leads, we can connect this IC PCB and printed circuit board. So this is called PCB. By using these leads, we can make connections with the circuits. Here you can see breadboard and remaining components. So this is called breadboard and this is called PCB. Here we can see thermistor IC. And these are the ceramic type of thermistors. So depending on the application, we can choose any one of the thermistor. So students, I will stop here for today and remaining topics we will see in next class.